All right, today we're going to be going over linear regression. So let's suppose we have xy pairs where we have x1, y1, x2, y2, and suppose that we have n data points total. And suppose that each xi is actually in itself a vector, m-dimensional vector, and y is an output, which is just a real number. We want to find some sort of relationship between x and y. So we want to find a function such that when you give me an x, I can give you a good approximation of y. And linear regression assumes that that relationship is linear. And I'll explain what I mean by that. So what I mean by that is that linear regression believes that y comes from some bias term plus a linear combination of the elements of x. So your w1 is your weight vector index. So you have w2 x2 plus w3 x3 plus ... wm all the way to the last dimension of xm, and then you can assume that you get some noise thrown into each observation. So this is the noise, and linear regression assumes that the mean of that noise is 0. This is random noise. And it also assumes that each noise in sample is independent. So that's the model that linear regression assumes, and what we're going to do is take a look at the bias term here. And we're going to remove this from our consideration of linear regression by just assuming that whenever you have an x vector, that before you put it into your linear regression algorithm, you're just going to prepend a 1 to the top of it. And that 1's going to end up being multiplied by this bias coefficient, so we can functionally treat our y's as if they're just coming from the transpose of a w vector times x plus the noise. We've gotten rid of the bias term by assuming that the vector has a 1 at the front of it. And this is a totally legitimate thing to do. So our goal in linear regression, is to find the best w that will explain the relationship given some set of data points, xi, yi, I equals 1 to n. So we want to find the best w given all those data points. And so one way that we might start to think about how to do this is to try to quantify how good or bad a particular choice of w is. And so one very natural way to do that is to take the mean over all the data points of the absolute value of the error. So your prediction minus the true value, wi. So if we take the mean of those errors, we get the name of this function, which is called the mean absolute error. And this function is known as a loss function. So we'll say that the loss for a particular choice of W is equal to this average of all the errors. And this particular choice is very intuitive, I think. It sort of seems the natural way to evaluate a linear model. Intuitive, but it does come with a drawback, and we'll get a little bit more into this later. This function, because of the absolute value, it's not differentiable. And all that means is it's not going to be easy for us to solve for our optimal W. And so because of that, a lot of times with linear regression, we choose a different loss function. Instead of the mean absolute error, we choose one that's differentiable. And that is the mean squared error. Whoops, xi transpose W minus yi squared. And this is just an alternative choice. It still measures the difference between what you think the output is and what the output actually is. So this is called the mean squared error. And this is differentiable. So what I want to do now is rewrite this loss function using matrix notation. So let's use matrix notation for this. It'll be easier for us to move forward with the linear algebra in this section if we think of our loss function for a particular choice of W in terms of matrix notation. So I claim that this loss function can be written as 1 over n times xw minus y transpose this entire matrix X now, consisting of all the data points, times xw minus y, where again, X is our data matrix. And it looks like this. Each data point is a row in the matrix. And our vector W is the same W. It's an m-dimensional vector. And Y is all the Y's in our data set. And just to show you that these two are actually equal, let's think about this term right here. So what exactly is that? Well, if we just take the first element of our data matrix, the first row, the first row times this column vector, when you're doing this matrix multiplication, it will give you the first element of your y vector. So if we're going to write xw minus y transpose, literally it's x1 transpose w minus y1 x2 transpose w minus y2 all the way to xn transpose w minus yn. And then we're multiplying it by its second term itself again, except not transpose. So we're going to be dotting it, taking the dot product of that with x1 transpose w minus y1 all the way down to xn transpose w minus yn. And hopefully you can see that when we take this dot product, it gives us, it's as if we were summing over all data points. And we're just taking xi transpose w minus yi, and we're squaring them. So hopefully you can see that, and that justifies this matrix way of writing a loss function. And so now that we have written our loss function in terms of matrices, now that we're thinking about matrices, let's take a minute to think about linear regression from a geometric standpoint. So suppose we have a column space of X consisting of the span of X's columns. So this is the column space of X, and we have, suppose that this is only two-dimensional, so X1 here, and dimension X2 here. And suppose we have Y that exists here. This is our Y vector. We can argue that the closest possible point to Y in the column space of X, that's actually XW. So we're trying to make XW as close to Y as possible by finding the choice of W that essentially projects this Y onto the column space of X. So whatever this is would be our W2, and then this value would be W1. So that's just a way to think geometrically about linear regression. Okay. Next, let's talk about how we solve for W given a data set. So we know that our loss function is equal to 1 over n, xw minus y transpose, xw minus y, and we want to find a W that minimizes this measure of error. So we want min over all possible W's of this loss function. And so one way that we can minimize a function, we learned from calculus, is to take the derivative and set that to 0. So suppose this is your function. We remember from high school that when you take the derivative and set it to 0, you'll get a max or a min, and in the case of a convex function, you'll get a min. And it happens that this function is convex. So convex. So all we have to do is to set the derivative of that to 0. And if you're not comfortable with taking derivatives of matrices and vectors, I suggest you read up on that a little bit, but you might be able to also gain some understanding of how that works if you just follow along. So we're going to take the derivative of the loss function with respect to W. So that equals the derivative of, and actually before I get into this, let me just say that we're going to drop this term 1 over n in our solving of the derivative, because if we minimize this entire loss function with respect to W, it doesn't matter if we have the 1 over n there, it's just a constant, it doesn't actually change the optimal W. So let's just drop that, and we'll say that we're minimizing the derivative of xw minus y transpose, xw minus y, again without the 1 over n, doesn't matter. And let's just expand this out a little bit. Just FOIL this. So W transpose X transpose XW minus 2 W transpose X transpose Y plus Y transpose Y dW, and we're going to take the derivative finally. So with respect to W, we're just going to distribute the derivative throughout the sum. So here we'll take the derivative of that first term, which ends up being 2x transpose xw. And the second term minus 2 x transpose y. We're taking the derivative with respect to W plus the derivative of y transpose y with respect to W, which that's just 0 because that's essentially a constant with respect to W. So if we're setting this to 0, to find the minimum, set to 0, we get that 2x transpose y equals 2x transpose x, w. And we can see that w equals x transpose x inverse, if we want to move that to the other side, times x transpose y. So this is w star because it's the w that minimizes the error of our linear regression mean squared error loss function. So minimizes error. And so this is the w that a computer program might return if you're running a simple form of linear regression. One last note about this, and this is just worth noting. X transpose x might not be invertible in some cases. And we know a result from linear algebra that says this happens when x does not have full column rank. So for example, if you have a data set that's really fat, meaning that it has many different features, but only a couple data points, that will be the case. And so most of the time, if you have enough data and you don't use too many features, this will be fine. You won't have to worry about it. But if this is the case, there is a small trick that you can do to make the first term be invertible. And that is to say that the optimal W is equal to x transpose x plus some really small number times the identity matrix. And this just ensures that this whole thing will be invertible. And that's actually related to something we'll talk about a little bit later. It's related to this concept of regularization. And we'll get to that later in our videos.